speed up their computation is to use operator fusion where you can, because as you saw, it took a few seconds for our model to just move from the CPU, which is the default, to the GPU. So we've got our architecture here, but of course we know that this potentially is wrong. And how would we find that out? Well, we could find the right hidden unit shape, or we could find that it's wrong by passing some dummy data through our model. So that's one of my favorite ways to troubleshoot a model. Let's, in the next video, pass some dummy data through our model and see if we've implemented the forward pass correctly, and also check the input and output shapes of each of our layers. I'll see you there. In the last video, we replicated the TinyVGG architecture from the CNN Explainer website, very similar to the model that we built in section 03, but this time we're using color images instead of grayscale images. And we did it quite a bit faster than what we previously did because we've already covered it, right? And you've had some experience now building PyTorch models from scratch, so we're going to pick up the pace when we build our models. But let's now go and try a dummy forward pass to check that our forward method is working correctly and that our input and output shapes are correct. So let's create a new heading. Try a forward pass on a single image. And this is one of my favorite ways to test the model. So let's first get a single image. Get a single image. We want an image batch. Maybe we get an image batch. Get a single image batch, because we've got images that are batches already. Image batch, and then we'll get a label batch, and we'll go next, iter train data loader symbol. That's the data loader that we're working with for now. And then we'll check image batch.shape and label batch.shape. Wonderful. And now let's see what happens. Try a forward pass. Oh, I spelled single wrong up here. Try a forward pass. We could try this on a single image. Trying it on the same batch will result in similar results. So let's go model 0, and we're just going to pass it in the image batch and see what happens. Oh no. Of course we get that input type, torch float tensor, and weight. Oh no. Of course we get that input type, torch float tensor, and weight type, torch CUDA float tensor should be the same, or input should be, so we've got tensors on a different device, right? So this is on the CPU, the image batch, whereas our model is of course on the target device. So we've seen this error a number of times. Let's see if this fixes it. Oh, we get another error, and we kind of expected this type of error. We've got runtime error, mat1 and mat2 shapes cannot be multiplied. 32, so that looks like the batch size. 2560 and 10. What is 10? Well, recall that 10 is the number of hidden units that we have. So this is the size here, that's 10 there. So it's trying to multiply a matrix of this size by this size. So 10 has got something going on with it. We need to get these two numbers, the middle numbers, to satisfy the rules of matrix multiplication, because that's what happens in our linear layer. We need to get these two numbers the same. And so our hint and my trick is to look at the previous layer. So if that's our batch size, where does this value come from? Well, could it be the fact that a tensor of this size goes through the flattened layer? Recall that we have this layer up here. So we've printed out the shape here of the conv block, the output of conv block 1. Now this shape here is the output of conv block 2. So we've got this number, the output of conv block 1, and then the output of conv block 2. So that must be the input to our classifier layer. So if we go 10 times 16 times 16, what do we get? 2,560. Beautiful. So we can multiply our hidden units, 10, by 16 by 16, which is the shape here, and we get 2560. Let's see if that works. We'll go up here, times 16 times 16, and let's see what happens. We'll rerun the model, we'll rerun the image batch, and then we'll pass it. Oh, look at that! Our model works! Well, the shapes at least line up. We don't know if it works yet. We haven't started training yet. But this is the output size. We've got the output. It's on the CUDA device, of course, but we've got 32 samples with 3 numbers in each. Now, these are going to be as good as random because we haven't trained our model yet. We've only initialized it here with random weights. So we've got 32, or a batch worth, of random predictions on 32 images. So you see how the output shape here, 3, corresponds to the output shape we set up here. Output shape equals length class names, which is exactly the number of classes that we're dealing with. But I think our number is a little bit different to what's in the CNN Explainer. 1616. How did they end up with 1313? You know what? I think we got one of these numbers wrong. Kernel size, stride, padding. Let's have a look. Jump into here. If we wanted to truly replicate it, Is there any padding here? I actually don't think there's any padding here. So what if we go back here and see if we can change this to 0 and change this to 0? 0. I'm not sure if this will work, by the way. If it doesn't, it's not too bad, but we're just trying to line up the shapes with the CNN explainer to truly replicate it. So the output of the conv block 1 should be 30, 30, 10. What are we working with at the moment? We've got 32, 32, 10. So let's see if removing the padding from our convolutional layers lines our shape up with the CNN explainer. So I'm going to rerun this, rerun our model. I've set the padding to 0 on all of our padding hyperparameters. Oh, and we get another error. We get another shape error. Of course we do, because we've now got different shapes. Wow, do you see how often that these errors come up? Trust me, I spend a lot of time troubleshooting these shape errors. So we now have to line up these shapes. So we've got 13, 13, 10. Now, does that equal 1690? Let's try it out. 13, 13, 10. 1690. Beautiful. And do our shapes line up with the CNN explainer? So we've got 30, 30, 10. Remember, these are in PyTorch, so color channels first, whereas this is color channels last. So yep, we've got the output of our first conv block is lining up here. That's correct. And then same with the second block. How good is that? We've officially replicated the CNN explainer model. So we can take this value, 13, 13, 10, and bring it back up here. 13, 13, 10. Remember, hidden units is 10, so we're just going to multiply it by 13, 13. You could calculate these shapes by hand, but my trick is I like to let the error codes give me a hint of where to go. And boom, there we go. We get it working again. Some shape troubleshooting on the fly. So now we've done a single forward pass on the model. We can kind of verify that our data at least flows through it. What's next? Well, I'd like to show you another little package that I like to use to also have a look at the input and output shapes of my model. And that is called Torch Info. So you might want to give this a shot before we go into the next video. But in the next video, we're going to see how we can use Torch Info to print out a summary of our model. So we're going to get something like this. So this is how beautifully easy Torch Info is to use. So give that a shot, install it into Google Colab, and run it in a cell here. See if you can get something similar to this output for our model 0. And I'll see you in the next video. We'll try that together. In the last video, we checked our model by doing a forward pass on a single batch, and we learned that our forward method so far looks like it's intact, and that we don't get any shape errors as our data moves through the model. But I'd like to introduce to you one of my favorite packages for finding out information from a PyTorch model, and that is Torch Info. So let's use Torch Info to get an idea of the shapes going through our model. So you know how much I love doing things in a programmatic way? Well, that's what Torch Info does. Before, we used print statements to find out the different shapes going through our model, and I'm just going to comment these out in our forward method so that when we run this later on during training, we don't get excessive printouts of all the shapes. So let's see what Torch Info does. And in the last video, I issued a challenge to give it a go. It's quite straightforward on how to use it, but let's see it together. This is the type of output we're looking for from our tiny VGG model. And of course, you could get this type of output from almost any PyTorch model. But we have to install it first. And as far as I know, Google Colab doesn't come with Torch Info by default. Now, you might as well try this in the future and see if it works. But yeah, I don't get this module because my Google Colab instance doesn't have it installed. No problem with that. Let's install Torch Info here. Install Torch Info, and then we'll import it if it's available. So we're going to try and import Torch Info. If it's already installed, we'll if it's Torch Info here. I don't get Torch Info by default. Now, you might as well try this in the future and see if it works. But yeah, I don't get this module because my Google Colab instance doesn't have it installed. No problem with that. Let's install Torch Info here. Install Torch Info, and then we'll import it if it's available. So we're going to try and import Torch Info. If it's already installed, we'll import it. And then if it doesn't work, if that try block fails, we're going to run pip install Torch Info, and then we will import Torch Info. And then we're going to run down here from Torch Info, import summary. And then if this all works, we're going to get a summary of our model. We're going to pass it in model 0, and we have to put in an input size here. Now that is an example of the size of the data that will flow through our model. So in our case, let's put in an input size of 1, 3, 64, 64. So this is an example of putting in a batch of one image. You could potentially put in 32 here if you wanted, but let's just put in a batch of a singular image. And of course, we could change these values here if we wanted to. 224, 224. But what you might notice is that if it doesn't get the right input size, it produces an error. There we go. So just like we got before when we printed out our input sizes manually, we get an error here. Because what Torch Info behind the scenes is going to do is it's going to do a forward pass on whichever model you pass it with an input size of whichever input size you give it. So let's put in the input size that our model was built for. Wonderful. So what Torch Info gives us is, oh, excuse me. Wonderful. So So let's put in the input size that our model was built for. Wonderful. So what Torch Info gives us size that our model was built for. Wonderful. So what Torch Info gives us is, oh, excuse me, we didn't comment out the printouts before. So just make sure we've commented out these printouts in the forward method of our TinyVGG class. So I'm just going to run this, then we run that, just to make sure everything still works. We'll run Torch Info, there we go. So no printouts from our model, but this is, look how beautiful this is. I love how this prints out. So we have our TinyVGG class, and then we can see it's comprised of 3 sequential blocks. And then inside those sequential blocks, we have different combinations of layers. We have some conv layers, some relu layers, some max pool layers, and then the final layer is our classification layer with a flatten and a linear layer. And we can see the shapes changing throughout our model as our data goes in and gets manipulated by the various layers. So are these in line with the CNN explainer? So if we check this last one, we've already verified this before. And we also get some other helpful information down here, which is total params. So you can see that each of these layers has a different amount of parameters to learn. Now, recall that a parameter is a value such as a weight or a bias term within each of our layers, which starts off as a random number. And the whole goal of deep learning is to adjust those random numbers to better represent our data. So in our case, we have just over 8,000 total parameters. Now, this is actually quite small. In the future, you'll probably play around with models that have 1 million parameters or more, and models now are starting to have many billions of parameters. And we also get some information here, such as how much the model size would be. Now, this would be very helpful depending on where we had to put our model. So what you'll notice is that as a model gets larger, has more layers, it will have more parameters, more weights and bias terms that can be adjusted to learn patterns in data. But its input size and its estimated total size would definitely get bigger as well. So that's just something to keep in mind if you have size constraints in terms of storage in your future applications. So ours is under 1 megabyte, which is quite small, but you might find that some models in the future get up to 500 megabytes, maybe even over 1 gigabyte. So just keep that in mind for going forward. And that's the crux of Torch Info, one of my favorite packages. It just gives you an idea of the input and output shapes of each of your layers. So you can use Torch Info wherever you need. It should work with most of your PyTorch models. Just be sure to pass it in the right input size. You can also use it to verify, like we did before, if the input and output shapes are correct. So check that out. Big shout out to Tyler Yep and everyone who's created the Torch Info package. Now, in the next video, let's move towards training our TinyVGG model. We're going to have to create some training and test functions. If you want to jump ahead, we've already done this. So I encourage you to go back to section 6.2 in the functionizing training and test loops. And we're going to build functions very similar to this, but for our custom data set. So if you want to replicate these functions in this notebook, give that a go. Otherwise, I'll see you in the next video and we'll do it together. How'd you go? Did you give it a shot? Did you try replicating the train step and the test step function? I hope you did. Otherwise, let's do that in this video, but this time we're going to do it for our custom data sets. And what you'll find is not much, if anything, changes because we've created our train and test loop functions in such a way that they're generic. So we want to create a train step function. And by generic, I mean they can be used with almost any model and data loader. So train step takes in a model and data loader and trains the model on the data loader. And we also want to create another function called test step, which takes in model and a data loader and other things and evaluates the model on the data loader. And of course, for the train step and for the test step, each of them respectively are going to take a training data loader. Oh, I just might make this a third heading so that our outline looks nice and beautiful. Section 7 is turning out to be quite a big section. Of course, we want them to be respectively taking their own data loader. So train takes in the train data loader, test takes in the test data loader. Without any further ado, let's create the train step function. Now we've seen this one in the computer vision section. So let's see what we can make here. So we need a train step, which is going to take in a model, which will be a torch nn.module. And we want it also to take in a data loader, which will be a torch.utils.data loader. And then it's going to take in a loss function, which is going to be a torch nn.module as well. And then it's going to take in an optimizer, which is going to be torch.optim.optimizer. Wonderful. And then what do we do? What's the first thing that we do in a training step? Well, we put the model in train mode. So let's go model.train. Then what should we do next? Well, let's set up some evaluation metrics, one of them being loss and one of them being accuracy. So set up train loss and train accuracy values. And we're going to accumulate these per batch because we're working with batches. So we've got train loss and train acc equals 0, 0. Now we can loop through our data loader. So let's write loop through data loader And we'll loop through each of the batches in this because we've batchified our data loader. So for batch XY in enumerate data loader, we want to send the data to the target device. So we could even put that device parameter up here. Device equals device. We'll set that to device by default. And then we can go X. Y equals x.toDevice and y.toDevice. Beautiful. And now what do we do? Well, remember the PyTorch, the unofficial PyTorch optimization song? We do the forward pass. So ypred equals model om x. And then number 2 is we calculate the loss. So calculate the loss. Let's go loss equals loss function. And we're going to pass it in ypred y. We've done this a few times now. So that's why we're doing it a little bit faster. So I hope you notice that the things that we've covered before, I'm stepping up the pace a bit. So it might be a bit of a challenge, but that's all right. You can handle it. And then, so that's accumulating the loss. So we're starting from 0 up here. And then each batch, we're doing a forward pass, calculating the loss, and then adding it to the overall train loss. And so we're going to optimize a 0 grad. So 0 the gradients of the optimizer for each new batch. And then we're going to perform back propagation. So loss backwards. And then 5, what do we do? Optimize a step, step, step. Wonderful. Look at that. Look at us coding a train loop in a minute or so. Now, let's calculate the accuracy and accumulate it. Calculate the... You notice that we don't have an accuracy function here? That's because accuracy is quite a straightforward metric to calculate. So we'll first get the ypred class because this is going to output model logits. As we've seen before, the raw output of a model is logits. So to get the class, we're going to take the argmax torch.softmax, so we'll get the prediction probabilities of ypred, which is the raw logits, what we've got up here, across dimension 1, and then also across dimension 1 here. Beautiful. So that should give us the labels. And then we can find out if this is wrong by checking it later on. And then we're going to create the accuracy by taking the ypred class, checking for equality with the right labels. So this is going to give us how many of these values equal true. And we want to take the sum of that, take the item of that, which is just a single integer, and then we want to divide it by the length of ypred. So we're just getting the total number that are right, and dividing it by the length of samples. So that's the formula for accuracy. Now we can come down here outside of the batch loop. We know that because we've got this helpful line drawn here. And we can go adjust metrics to get the average loss and accuracy per batch. So we're going to set train loss is equal to train loss divided by the length of the data loader, so the number of batches in total. And the train accuracy is the train acc divided by the length of the data loader as well. So that's going to give us the average loss and average accuracy per epoch across all batches. So train acc. Now that's a pretty good looking function to me for a train step. Do you want to take on the Now, that's a pretty good looking function to me for a train. So train acc. Now, that's a pretty good looking function to me for a train step. Do you want to take on the test step? So pause the video, give it a shot, and you'll get great inspiration from this notebook here. Otherwise, we're going to do it together in 3, 2, 1. Let's do the test step. So create a test step function. So we want to be able to call these functions in an epoch loop. And that way, instead of writing out training and test code for multiple different models, we just write it out once and we can call those functions. So let's create def test step. We're going to do model, which is going to be, if I could type, torch nn module. And then we're going to do data loader, which is torch utils.data.data loader. Capital L there. And then we're going to just pass in a loss function here because we don't need an optimizer for the test function. We're not trying to optimize anything. We're just trying to evaluate how our model did on the training data set. And let's put in the device here. Why not? That way we can change the device if we need to. So put model in eval mode because we're going to be evaluating or we're going to be testing. Then we can set up test loss and test accuracy values. So test loss and test acc. We're going to make these 0. We're going to accumulate them per batch. But before we go through the batch, let's turn on inference mode. So this is behind the scenes going to take care of a lot of PyTorch functionality that we don't need. It's very helpful during training, such as tracking gradients. But during testing, we don't need that. So loop through data loader or data batches. And we're going to go for batch x, y in enumerate data loader. You'll notice that above, we didn't actually use this batch term here. And we probably won't use it here either, but I just like to go through and have that there in case we wanted to use it anyway. So send data to the target device. So we're going to go x, y equals x.to device, and same with y.to device. Beautiful. And then what do we do for an evaluation step or a test step? Well, of course, we do the forward pass, and we're going to, let's call these test pred logits and get the raw outputs of our model. And then we can calculate the loss on those raw outputs, calculate the loss. We'll get the loss is equal to loss function on test pred logits versus y. And then we're going to accumulate the loss. So test loss plus equals loss.item. Remember, item just gets a single integer from whatever term you call it on. And then we're going to calculate the accuracy. Now, we can do this exactly how we've done for the training dataset or the training step. So test pred labels, we're going to, I just want to highlight the fact that you actually don't need to take the softmax here. You could just take the argmax directly from this. The reason why we take the softmax, so you could do the same here. You could just directly take the argmax of the logits. The reason why we get the softmax is just for completeness. So if you wanted the prediction probabilities, you could use torch. I just want to highlight the fact that you actually don't need to take the softmax here. You could just take the argmax directly from this. The reason why we take the softmax, so you could do the same here. You could just directly take the argmax of the logits. The reason why we get the softmax is just for completeness. So if you wanted the prediction probabilities, you could use torch.softmax on the prediction logits, but it's not 100% necessary to get the same value. And you can test this out yourself. So try this with and without the softmax and see if you get the same results. So we're going to go test accuracy plus equals. Now we'll just create our accuracy calculation on the fly. Test pred labels, we'll check for equality on the y, and then we'll get the sum of that, we'll get the item of that, and then we'll divide that by the length of the test pred labels. Beautiful. So it's going to give us accuracy per batch. And so now we want to adjust the metrics to get average, loss, and accuracy per batch. So test loss equals test loss divided by length of the data loader, and then we're going to go test acc equals test acc divided by length of the data loader, and then finally we're going to return the test loss, not lost, and test accuracy. Woohoo! Look at us go. Test loss, not lost, and test accuracy. Woohoo! Look at us go. Now, in previous videos, in previous sections, that took us a fairly long time, but now we've done it in about 10 minutes or so. So give yourself a pat on the back for all the progress you've been making. But now, let's in the next video, we did this in the computer vision section as well. Did we create a train function? Oh no, we didn't, but we could. So let's create a function to functionize this. We want to train our model. I think we did actually, def train. We've done so much, I'm not sure what we've done. Oh, okay. So looks like we might not have, but in the next video, give yourself this challenge, create a function called train that combines these two functions and loops through them both with an epoch range. So just like we've done here in the previous notebook, can you functionize this? So just this step here. So you'll need to take in a number of epochs, you'll need to take in a train data loader and a test data loader, a model, a loss function, an optimizer, and maybe a device. And I think you should be pretty on your way to all the steps we need for train. So give that a shot, but in the next video, we're going to create a function that combines train step and test step to train a model. So on the test step, so pause the video, give it a shot, and you'll get great inspiration from this notebook here. Otherwise, we're going to do it together in 3, 2, 1. Let's do the test step. So create a test step function. So we want to be able to call these functions in an epoch loop. And that see calculation on the fly. Back for all the progress you've been making. But, oh no, we didn't. That combines these two functions and loops through them both with an epoch range. So just like we've done here in the previous notebook, can you functionize this? So just this step here. So you'll need to take in a number of epochs, you'll need to take in a train data loader and a test data loader, a model, a loss function, an optimizer, and maybe a device. And I think you should be pretty on your way to all the steps we need for train. So give that a shot, but in the next video, we're going to create a function that combines train step and test step to train a model. I'll see you there. How'd you go? In the last video, I issued you the challenge to combine our train step function as well as our test step function together in their own function so that we could just call one function that calls both of these and train a model and evaluate it, of course. So let's now do that together. I hope you gave it a shot. That's what it's all about. So we're going to create a train function. Now, the role of this function is going to, as I said, combine train step and test step. Now, we're doing all of this on purpose, right? Because we want to not have to rewrite all of our code all the time. So we want to be functionizing as many things as possible so that we can just import these later on if we wanted to train more models and just leverage the code that we've written before as long as it works. So let's see if it does. We're going to create a train function. I'm going to first import tqdm.auto, because I'd like to get a progress bar while our model is training. There's nothing quite like watching a neural network train. So step number one is we need to create a train function that takes in various model parameters, plus optimizer, plus data loaders, plus a loss function, a whole bunch of different things. So let's create def train, and I'm going to pass in a model here, which is going to be torch and then .module. You'll notice that the inputs of this are going to be quite similar to our train step and test step. I don't actually need that there. So we also want a train data loader for the training data, torch.utils.data.dataloader. And we also want a test data loader which is going to be torch.utils.data.data loader. And then we want an optimizer. So the optimizer will only be used with our training data set, but that's okay. We can take it as an input. Optimizer. And then we want a loss function. This will generally be used for both our training and testing step, because that's what we're combining here. Now, since we're working with multi-class classification, I'm going to set our loss function to be a default of nn.cross-entropy-loss. Then I'm going to get epochs. I'm going to set 5. We'll train for 5 epochs by default. And then finally, I'm going to set the device equal to the device. So, what do we get wrong here? That's all right. We'll just keep coding. We'll ignore these little red lines. If they stay around, we'll come back to them. So, step number 2. I'm going to create, this is a step you might not have seen, but I'm going to create an empty results dictionary. Now, this is going to help us track our results. Do you recall in a previous notebook, we outputted a model dictionary for how a model went? To help us track our results. Do you recall in a previous notebook, we outputted a model dictionary for how a model went? So if we look at model 1 results, yeah, we got a dictionary like this. So I'd like to create one of these on the fly, but keep track of the result every epoch. So what was the loss on epoch number 0? What was the accuracy on epoch number 3? So we'll show you how I'll do that. We can use a dictionary and just update that while our model.
And streets twinkling with joy. There's magic in the air, or is that snow? Here in Trafalgar Square, in the heart of the city, a winter wonderland has been created just for the day.
It's a lovely snowy day, isn't it?
Father Christmas has dropped by for the wintry fun, and London's town crier is in fine form as he passes out mince pies and holiday cheer. Nearby at Somerset House, once a grand palace, the courtyard has been transformed into an ice skating rink, elegant enough to make a commoner feel like royalty. At Covent Garden, shoppers can find classic toys for tots at Benjamin Pollock's famous toy shop, in business since the 1880s. The joy and peace of the Christmas season bring both people and countries together. This giant spruce, a gift from the citizens of Oslo, is a reminder of the friendship forged between Britain and Norway during World War II. And Norway is where we're headed next. Here in small-town Norway, Christmas is celebrated with a unique intimacy and a
model trains. So results, I want to keep track of the train loss. So I'm going to set that equal to an empty list and just append to it. I also want to keep track of the train accuracy. We'll set that as an empty list as well. I also want to keep track of the test loss. And I also want to keep track of the test accuracy. Now, you'll notice over time that what you can track is actually very flexible, and what your functions can do is also very flexible. So this is not the gold standard of doing anything by any means. It's just one way that works. And you'll probably find in the future that you need different functionality. And of course, you can code that out. So let's now loop through our epochs. So for epoch in TQDM, let's create a range of our epochs above. And then we can set the train loss. Have I missed a comma up here somewhere? Type annotation not supported for that type of expression. Okay, that's all right. We'll just leave that there. So we're going to go train loss and train acc. Recall that our train step function that we created in the previous video, train step returns our train loss and train acc. So as I said, I want to keep track of these throughout our training. So I'm going to get them from train step. Then for each epoch in our range of epochs, we're going to pass in our model and perform a training step. So the data loader here is of course going to be the train data loader. The loss function is just going to be the loss function that we pass into the train function. And then the optimizer is going to be the optimizer. And then the device is going to be device. Beautiful, look at that. We just performed a training step in 5 lines of code. So let's keep pushing forward. It's telling us we've got a whole bunch of different things here. Epochs is not defined. Maybe we just have to get rid of this. We can't have the type annotation here. And that'll stop Google Colab getting angry at us. If it does anymore, I'm just going to ignore it for now. Epochs. Anyway, we'll leave it at that. We'll find out if there's an error later on. Test loss, you might be able to find it before I do. So test step, we're going to pass in the model. We're going to pass in a data loader. Now this is going to be the test data to load up. Woohoo, look at us go. Great. Here is, of course, and then we don't need an optimal. We're just going to pass in the device, and then behind the scenes, both of these functions are going to train and test our model. How cool is that? So still within the loop, right? This is important. Within the loop, we're going to have number 4 is we're going to print out. Let's print out what's happening. Print out what's happening. We can go print, and we'll do a fancy little print statement here. We'll get the epoch, and then we will get the train loss, which will be equal to the train loss. We'll get that to, let's go 4 decimal places. How about that? And then we'll get the train accuracy, which is going to be the train ac. We'll get that to 4. Maybe 3 decimal 4, just so it looks nice, looks aesthetic. And then we'll go test loss. We'll get that coming out here, and we'll pass in the test loss. We'll get that to 4 decimal places as well. And then finally, we'll get the test accuracy. So a fairly long print statement here, but that's all right. We'd like to see how our model's doing while it's training. Beautiful. And so again, still within the epoch, we want to update our results. Doing while it's training. Beautiful. And so again, still within the epoch, we want to update our results dictionary so that we can keep track of how our model performed over time. So let's pass in results. We want to update the train loss. And so this is going to be this. And then we can append our train loss value. So this is just going to expend the list in here with the train loss value every epoch. And then we'll do the same thing on the train accuracy, append train ac. And then we'll do the same thing again with test loss. Dot append test loss, and then we will finally do the same thing with the test accuracy. Test accuracy. Now this is a pretty big function, but this is why we write the code now so that we can use it multiple times later on. So return the filled results at the end of the epoch, so outside the epoch's loop. So our loop, we're outside it now. Now let's return results. Now, I've probably got an error somewhere here, and you might be able to spot it. Okay, train data loader. Where do we get that invalid syntax? Maybe up here? Oh, we don't have a comma here. Was that the issue the whole time? Wonderful. You might have seen that. I completely missed that. But we now have a train function to train. Now, multiple times, and then loss. See, expand the list in here, in loss, and dot test POC. So you might have seen that. I'm completely missed that, but we now have a train function to train our model. And the train function, of course, is going to call out our train step function and our test step function. So what's left to do? Well, nothing less than train and evaluate model 0. So our model is way back up here. How about in the next video, we leverage our functions, namely just the train function, because it's going to call our train step function and our test step function and train our model. So I'm going to encourage you to give that a go. You're going to have to go back to the workflow maybe, or maybe you already know this. So what have we done? We've got our data ready and we turned it into tensors using a combination of these functions. We've built and picked a model. Well, we've built a model, which is the TinyVGG architecture. Have we created a loss function yet? I don't think we have. Or an optimizer. I don't think we've done that yet. We've definitely built a training loop though. We aren't using torch metrics, we're just using accuracy, but we could use this if we want. We haven't improved through experimentation yet, but we're going to try this later on. And then save and reload the model. We've seen this before. So I think we're up to picking a loss function and an optimizer. So give that a shot. In the next video, we're going to create a loss function and an optimizer, and then leverage the functions we've spent the last 2 videos creating to train our first model, model 0, on our own custom data set. This is super exciting. I'll see you in the next video. Who's ready to train and evaluate model 0? Put your hand up. I definitely am, so let's do it together. We're going to start off section 7.7, and we're going to put in train and evaluate model 0, our baseline model on our custom data set. Now, if we refer back to the PyTorch workflow, I issued you the challenge in the last video to try and create a loss function and an optimizer. I hope you gave that a go, but we've already built a training loop. So we're going to leverage our training loop functions, namely train, train step, and test step. All we need to do now is instantiate a model, choose a loss function and an optimizer, and pass those values to our training function. So let's do that. All right, this is so exciting. Let's set the random seeds. I'm going to set torch manual seed 42 and torch CUDA manual seed 42. Now remember, I just want to highlight something. I read an article the other day about not using random seeds. The reason why we are using random seeds is for educational purposes. So to try and get our numbers on my screen and your screen as close as possible. But in practice, you quite often don't use random seeds all the time. The reason why is because you want your model's performance to be similar regardless of the random seed that you use. So just keep that in mind going forward. We're using random seeds to just exemplify how we can get similar numbers on our page. But ideally, no matter what the random seed was, our models would go in the same direction. That's where we want our models to eventually go. But we're going to train for 5 epochs, and now let's recreate an instance of TinyVGG. We can do so because we've created the TinyVGG class. So TinyVGG, which is our model 0. We don't have to do this, but we're going to do it anyway, just so we've got all the code in one place. TinyVGG, what is our input shape going to be? That is the number of color channels of our target images. And because we're dealing with color images, we have an input shape of 3. Previously, we used an input shape of 1 to deal with grayscale images. I'm going to set hidden units to 10 in line with the CNN Explainer website. And the output shape is going to be the number of classes in our training data set. And then, of course, we're going to send the target model to the target device. So what do we do now? Well, we set up a loss function and an optimizer. Loss function and optimizer. So our loss function is going to be, because we're dealing with multi-class classification, NN cross entropy, if I could spell, cross entropy loss. And then we're going to have an optimizer. This time, how about we mix things up? How about we try the Atom optimizer? Now, of course, the optimizer is one of the hyperparameters that you can set for your model, and a hyperparameter being a value that you can set yourself. So the parameters that we want to optimize are our model 0 parameters. And we're going to set a learning rate of 0.0. To optimize our model 0 parameters, and we're going to set a learning rate of 0.001. Now recall that you can tweak this learning rate if you like, but I believe, did I just see that the default learning rate of Atom is 0.001? Yeah, there we go. So Atom's default learning rate is 1 to the power of 10 to the negative 3. And so that is the default learning rate for Atom. And as I said, oftentimes different variables in the PyTorch library, such as optimizers, have good default values that work across a wide range of problems. So we're just going to stick with the default. If you want to, you can experiment with different values of this. But now let's start the timer because we want to time our models. We're going to import from timet. We want to get the default timer class, and I'm going to import that as timer just so we don't have to type out default timer. So the start time is going to be timer. This is going to just put a line in the sand of what the start time is at this particular line of code. It's going to measure that, and then we're going to train model 0. Now, this is using, of course, our train function. So let's write model 0 results. I only wrote model 1, but we're not up to there yet. So let's go train model equals model 0. And this is just the training function that we wrote in a previous video. And the train data is going to be our train data loader. And we've got train data loader simple because we're not using data augmentation for model 1. And then our test data loader is going to be our test data loader simple. And then we're going to set our optimizer, which is equal to the optimizer we just created, the friendly Atom optimizer. And the loss function is going to be the loss function that we just created, which is NN cross entropy loss. Finally, we can send in epochs is going to be num epochs, which is what we set at the start of this video to 5. And of course, we could train our model for longer if we wanted to, but the whole idea of when you first start training a model is to keep your experiments quick. So that's why we're only training for 5. Maybe later on you train for 10, 20, tweak the learning rate, do a whole bunch of different things. But let's go down here. Let's end the timer, see how long our model took to train. End the timer and print out how long it took. So in a previous section, we created a helper function for this. We're just going to simplify it in this section. We're just going to print out how long the training time was. Total training time. Let's go end time minus start time, and then we're going to go we'll take it to 3 decimal places, hey? Seconds. You ready to train our first model, first convolutional neural network on our own custom data set on pizza, steak, and sushi images. Let's do it. You ready? 3, 2, 1. No errors. Oh, there we go. Okay. Should this be trained data loader? Did you notice that? What does our trained data take as input? Oh, we're not getting a doc string. Oh, there we go. We want trained data loader. Data loader. And same with this, I believe. Let's try again. Beautiful. Oh, look at that lovely progress bar. Okay, how's our model is training quite fast. Okay, all right, what do we get? So we get an accuracy on the training data set of about 40%, and we get an accuracy on the test data set of about 50%. Now, what's that telling us? It's telling us that about 50% of the time our model is getting the prediction correct, but we've only got 3 classes. So even if our model was guessing, it would get things right 33% of the time. So even if you just guessed pizza every single time, because we only have 3 classes, if you guess pizza every single time, you get a baseline accuracy of 33%. So our model isn't doing too much better than our baseline accuracy. Of course, we'd like this number to go higher, and maybe it would if it trained for longer. So I'll let you experiment with that, but if you'd like to see some different methods of improving a model, recall back in section number 02, we had an improving a model section, improving a model. Here we go. So here's some things you might want to try. We can improve a model by adding more layers, also add more here spoken case, default, to help these first longer. Results. This is a good way to inspect how our model is training. Yeah, so we've got some values here.